And what? So correlation exists between two variables when the values of one variable are somehow associated with the values of the other. So let me go back. I just turned that little recording on. Let me be clear where we're at. We're in 2.4, scatter plots, correlation, regression. Okay. So I jumped ahead. Here we go. So correlation exists when there's a relationship. So if two things correlate, they relate to each other. They have something to do with one another. And then a linear correlation means they relate to each other in a line fashion, in a straight line fashion. So let's see some examples. And then a scatter plot is a bunch of dots on a graph that help you see if there's a correlation or not. Here's a picture. Here's our first example. That's a scatter plot. So what that is, this is waist circumference, arm circumference. Do you understand? They just took a whole bunch of people. They measured the circumference of their waist, all the way around their waist, and the circumference of their arm. I don't know if it's forearm or upper arm or what. But they did some kind of medical thing where they just measured waist, measured arm, put them on a graph, right? So maybe, a person has an arm of a certain, whatever, centimeters circumference, and then, it's the waist this way, and the arm that way. So, for example, let me make sure this data is making sense for you. So suppose there's a dot like here. What is that dot that's way up there? That person has a waist that is, I don't know what that is, maybe 170 centimeters around. I have no feel for centimeters, so whatever. So 170 centimeters around, and their arm is 45 centimeters around their arm. Maybe that's upper arm. I don't know. Is 45 centimeters around. Okay? That's not one dot. That's one person. That one dot is one person's waist, arm circumferences. Circumference just means around, right? Around the outside. So let's say this dot right here. What does that mean? This person has 130 about around their waist, and they're at what, like 34, maybe 33 around their upper arm. Make sense on that? So like a bodybuilder. I had a roommate when I was at college at Cal Poly. He was a bodybuilder. So they aim to have where would they be on the graph? Where would they want to be? Lower left, upper right, upper left, lower right. Where would they aim to be? My old buddy Mitch, where would he aim to be? On the
smaller waist.
So that small waist, big upper arm. So where would that be?
Left and up.
It's small waist, so left.
Up all the way.
Up. Yeah, they'd want to be left up. They'd want to be somewhere up here, right? Because that'd be a small waist, big arm circumference, right? So getting the idea on the data. So all those dots are people. They're people. And what we're wondering, why would we put all those dots? This is like, I don't know, how many dots are up there? Maybe 100 people, and they just smatter the dots. Just take their data, put it in a computer, and a computer just spit. This is what people really do. This is what statisticians do. When they're wondering, like a medical person might wonder, is there a relationship between waist circumference and arm circumference, waist size and arm size? Is there a general relationship among people? Well, they would have the computer just spit out this data, right? Person by person, just smatter these dots down and scatter plot. And then they would just look at them and go, do those look like they would relate in a line specifically? Does it look like it's a line? I would say sort of. It looks like it's kind of like the best. We're going to get to this in just a second. That would be what's called the best fit line. That's the line that fits best that data. It goes through the middle of the data, basically. It looks kind of linear to me. It looks like, it does seem to move up or right. I would say there is some correlation there. Bigger waist, bigger arms tend to go together. So whereas what if the data came out that way? No relationship. That's just no relation. They're not. Those dots aren't headed in any direction, right? There seems to be no relationship. If that's the data of weight, that's the way we changed. I thought we were doing the same thing. Weight and pulse rate. So how much somebody weighs and what their pulse rate is seems to be unrelated. No relationship. That makes sense? Those dots have no pattern or direction at all. No correlation. Whereas the last one, correlation, the distinct pattern of the plotted points, it's hard to read, suggests that there is a correlation between waist circumference and arm circumference. Yeah. Whereas that's no relationship, no correlation. Next one. Now, there's something you calculate, which we'll get into. Well, really, we'll just take computer output is what we'll do. It's pretty complex. You just have a computer do it. Linear correlation coefficient, R. So this is what statisticians do. And you'll read studies, likely, in your job. You may read studies. It's pretty common. You don't have to be like super high level. This is pretty commonly used. They'll say such and such was measured, and the linear correlation coefficient R was boom. And so you want to know, what does that mean? Well, here's specifically what it means. If you have an R value very close to -1 or +1, that means there does appear to be a linear correlation. If your R value is very close to 0, there's no relationship. +1 means it's going up. That's supposed to be R. R is +1. R -1, the relationship is a negative relationship. Does that make sense? Where R equals 0 means, there's just nothing. Nothing. No line. I should say no line. The data does not appear to have a linear relationship. So like back here, right? Is this line positive slope or negative slope? Is it positive? But isn't that line going down? I'm trying to fool you right now. I just want to make sure you don't get fooled on the test. Yeah, because you think, well, it goes up and down. How do you know which one? What's the rule in math? What do we always do? As you go to the right. I just want to make sure you're good and don't suddenly freeze on the test like, hey, that line's going both ways. I never thought about it carefully before. As you go to the right. As you go to the right. So we always mean as you go to the right, that line goes up. So that's positive slope, like you first thought before I tried to fool you, right? So that one's positive. So that R value, if you had a computer calculator, it'd probably be something like 0.89 or almost 1. We'll write some more of this in a minute. The closer it is to +1, the closer the dots. If they were tighter in a line, it would be even higher. The closer it is to +1, the more the data seem to fit a line, seem to have a linear relationship. This one, R would be, approximately 0. It'd be something like 0.13 or something that's basically 0. Or maybe it'd be -0.09. Who knows? It'd be basically 0. It wouldn't be close to 1 or -1. There's no relationship there. There's no linear relationship. Okay, so here we go. Here's some more data. Correlation between shoe print lengths and height. Like how big your shoe is versus how high you are. How tall you are. Yeah, so how big your shoe is and how tall you are, what your height is. All right. How would you, that's not much data. I mean, that's only 1, 2, 3, 4, 5. So, but you see how they're doing that? They took this point right here, 29.7. That's this point. See, no, that's not that point. That's shoe print 29. That must be these, huh? Yeah. That's almost 30. And 175.3. That's this one. And the other one, 29.7, 177. So that's a person that had shoe print length 29.7. One of them was 178 centimeters tall. And the other person was 176 centimeters tall. And then this whoops, thing's bouncing around on me here. 31.4 is how long they're, that'd be 31.4, where's that? Right here. And they came out 185. They're real tall. So anyway, that's how they're getting the data. Is that making sense? How they got those 5 data points? They're X, Y dots on a graph. Shoe print, length, and height. Now, is there a relationship there? Maybe. It's not much data. You'd want more data. Sort of looks like it is kind of going like a line. But you'd want more data. So here's what they did. They spit it into, this is StatDisk, what Brian's been talking about. You know that program? No, StatCrunch. So what's StatDisk? That's something different than the other one? It's a different one. Okay, they have like several.
They also have one called Minitabs.
Yeah, right. All connected with this software that we have?
No, just StatCrunch is.
Just StatCrunch is. Oh, okay. Thank you, Brian. So StatPlot's some other program. Anyway, there's a million stats programs out there. Basically, part of this class is we'll teach you how to read the output generally from stat output or read an article. And so one of the things, so here we are, we're beginning. One of these is the kind of thing you'd read. Here's where you want to hone in. Correlation coefficient R, 0.59. So right there, 0.5. Now, what does that mean? That's R is 0.591. I'll just round it. 0.591. Now, if you put a scale, remember -1 and +1, here's 0 in the middle. That's about this data. They basically took these 5 data points, right here, these 5 red dots, which all came from this table of data, right? And they spit them into a computer, well, they typed them into a computer, and they said, computer, tell me the R value, calculate. We'll do that on our graphing calculators. I hope you have one that's coming on that slow boat from China. We'll be using those maybe next week, right? $40 to $50. We'll type in a bunch of data and boom, and it'll give us an R value. We'll also look at output from other things. Anyway, so they did that. They stuck those points in, clicked R, and it told them 0.59. Now, where's 0.59? It's about right there, 0.591. So it's not getting very close to 1, is it? I mean, it's about halfway there. So it's not very strong data. You want to be close. To really be convinced that two things have a linear relationship, you want to be closer than that. So that's not the best. That's not getting very close to +1. See what I mean? It's how to read and understand that data. If it came out something like 0.89, which is almost there, then we'd say there's strong evidence that these two things have a linear relationship. 0.59, there's weak evidence, nothing strong. Making sense? So right there, that's what that means. If you read an article and they measured 2 quantities and they plugged them into a computer and got the correlation, the linear correlation coefficient R, 0.591, that's not very strong evidence. All right, on we go. P-value. This is probably the most important thing we'll use in the whole course. P-value. Not that we're going to get it all right now. We'll be growing in our understanding of p-value throughout the course. But here's the beginning. This is the beginning of p-value. If there really is no linear correlation between 2 variables, the p-value is the probability, P stands for probability of getting paired sample data with a linear correlation coefficient R that is at least as extreme as the one obtained from the paired sample data. That was a lot of fancy words, huh? You wouldn't want to be tested on that. Just from that. Let me clean that up. Let me say that more simply. P stands for probability. It's the probability that the results, that the study results, the data study results, that the data study results were just luck. Is that more simple? Because that's the problem, huh? Anytime you're measuring anything in statistics, like statistics is important. Because like for medicine especially, right? How do they know if a new cancer treatment, let's talk about something serious. How do they know if a new cancer treatment works? How do they know? Well, they keep a record, right? They keep information. They keep data. But the problem is luck could always get in there, right? If you gave it to 100 patients, say you gave it to 20 patients and their average lifespan increased by 2 years, could that have just been luck? Could it have been that those 20 patients just happened to be healthier than the average 20 patients? You just happened to get a lucky batch. The medicine isn't really doing anything better. It was just a lucky group of 20 patients. Could that be? Maybe. But what if you grabbed 100 patients and the average lifespan went up by 5 years instead of just 2 years? Or what if you grabbed 1,000 patients and the average lifespan went up by 5 years? Could that be luck? Well, yeah, it could be, but really unlikely. And you would tend to believe the results are real. The medicine's really doing something, right? You would tend to rule out luck. So that's statistics in a nutshell. Can we get rid of luck? That's so much of what we're going to do in here. Is we're going to look at results and we're going to say, do we believe that whatever, that medicine, those glasses, that surgery, that whatever is really doing something, or was it just luck? Because, things can happen luckily in life, right? You get a lucky 20 people, but you probably can't get a lucky 1,000 people. You know what I mean? Does that make sense? And what will tell you that is the p-value. That's the chance, the probability that it was just luck. So if your p-value comes out super small, like 0.00013, you think the chance of luck is super small. That medicine must be really working. It can't be luck, right? We believe, so that's a low chance of luck. We believe the medicine's working. That's a low chance of luck. But what if the probability comes out to be 0.17? Now you might feel like that's low, but in the statistics world, that's not considered low. That's 17%, right? That's basically the same as 17%. There's a 17% chance that the results were just lucky. Now you might think, well, that's pretty good. Well, yeah, it's okay, but you wouldn't want to bet your life on it, right? If it's only 17%. Could the medicine be good? It could, but we just haven't proven it yet. 17% chance of luck is too much. Well, how low do they want it? Does anybody know? 5. 5 is considered the general bar in statistics. We'll get to that next. This one came out, this p-value 0.294. That's 29.4%. It's right, where is it? There, right there. See the p-value on that data output? 0.29369. They rounded it to 0.294. That's 29.4% chance of luck. It's almost a 30% chance that they just happen to get a lucky group. That's not strong. That's not strong evidence. So how good? So as we conclude, there's not sufficient evidence. We don't believe there's a linear relationship there. So how small? 5% or less, like we were saying. That's when we get results that say there was less than a 5% chance that was just luck, we tend to believe those results. That's strong, what we call strong evidence. That it wasn't just, could it still have been luck? Yeah, it could, but it's very unlikely. It's probably, the data is telling us the truth. It's probably the medicine or the whatever is really having an effect. All right, so let's try another one. Here's more data. So now they measured some more. So what do you do when you get data that's not convincing? You go out and get some more data, and you try to find some more about the story. So here's some more data. Here's a whole bunch more dots. Now, is this stronger? Suppose they run the Pearson correlation shoe print height thing. They get 0.813. I don't even know. Oh, yeah, that's the R. That's the R value right there. So this is our R. And this, more importantly, look at that p-value. That's as low as she goes. That's 0. That's a 0%. Now, there's always really some slim chance of luck, but that's, as far as the computer could calculate this one, there's basically no chance of luck. Look at that data. It looks like a line fits right through there, doesn't it? So we would say, yeah, how long your shoes are is definitely related to your height, which makes sense, doesn't it? In general, there's a relationship there. There's some people that have really big feet and aren't tall, or vice versa, really small feet and are tall, but not usually. Generally, the bigger your feet, the taller you are. There is a relationship there, is what that data is saying. Make sense? Very little chance of luck. Okay, so and that's what they're saying here. R is 0.813. That's pretty strong. That's close to 1. So you see the two different numbers we're looking at. Well, you want R close to 1, 1.0, and you want P small. That's what we got, a small p and an R close to 1. They both say, it looks like there's a linear relationship here. R is closer to, positive means an upward slope. Yeah. So if it was negative, it'd be downward. That's right. All right. Regression. So now we want to say, hey, can we fit a line? The line of best fits called the regression line. So when you have a scatter plot, a bunch of data, you want to fit a line. So if you say, hey, I think there is a relationship here. I think, the bigger your feet, the taller you are. What do doctors like to do? They like to predict based upon juniors, whatever. I think they do it by spine, don't they? But sometimes they use feet. Is there a relationship? Can we predict how tall somebody's going to be? They use things to do that, don't they? They use data. Just this weekend, I was at a soccer tournament, and I was talking to one of the moms. Her son plays water polo for high school, and he's 15 years old, and he's 5'9" or 10 now, 15 years old, and they were predicting his height, and they were saying, he's only going to be 5'11" or 6 foot probably. I guess you're supposed to be 6'2" to get a scholarship for water polo. I don't know. I'm not in the neighborhood, or any of my kids, are getting a scholarship for water polo. But anyway, so the doctor was telling this mom, she was telling us just yesterday, or sitting around at the soccer tournament talking about our kids, and her son, she wants her son to get a scholarship. She doesn't think he has a very good chance of getting a scholarship for water polo when he's a senior, because he's not projected to get that tall. How do doctors do that? They're going on statistical data. That's what they're doing. And they do things like this. They look at data from shoe lengths or things with the spine, and they figure out, does that predict height? Well, we saw that data, we saw those dots, and then they take all those dots and they try to fit a line through the middle. It's called the best fit line, or it's also called the regression line. So that's what we're saying here. The regression line, or the line of best fit, or it's also called it has a lot of names. It goes by the least squares line, the regression line, the line of best fit. You get the equation of the line. That's like y equals mx plus b kind of thing, except they put the mx at the back. Right? It's like a line equation from algebra. You know what I mean? It's the line that fits the best through the middle of the dots. Okay, so there it is. They did a better job on the line than me. There's the best fit line. Computers will calculate this for us. You just put in the data, hit the button, the computer cranks out the line that fits the best through the middle of the data, gives you that relationship, and then you have an equation. Do you know what I mean by an equation? You have something like y, let me just make one up, 3x plus 2 or whatever. And that means you could put in somebody's, so you can measure a kid's shoe size, maybe at age 14, plug that in for x, and that would predict how tall they're going to be, their maximum height. That's the kind of relationship you could get. That's how they do that. I mean, we're not getting specific yet. I'm just keeping it general. But we're going to get more specific later, not in this section. This is just chapter 2 is just overview, and then we'll dive into details, chapter 3 and beyond. Okay, so here, how would it look? How does the output on a computer look? Well, here it is. Here's the R value. That's a pretty good R value, almost 1. Here's the p-value, 0, so we believe there's strong evidence, very little chance of luck. Probability of luck, basically 0. So here's the regression line. The B0 is right there, 80.93. The B1, that's like the slope, 3.21. So 80.9, they rounded 3.22, x. There's the equation of the line that fits this. So computer will spit that out, and then you can use that equation. Now, here's how they would use it. Y is height, in this problem, y is height, and x is shoe print length. So basically, you could plug in your shoe print length, multiply by 3.22, add 80.9, and you get your height, predicted height, in centimeters. It's centimeters, I think, right? Wasn't this all centimeters? That's a formula. See how we crank that out from data and believe it's reliable because the chance of luck is very low? That's what people are doing in the medical world. They're going on data. They don't have some other magic thing. They're using data. That's all they're doing. So we're uncovering and understanding what they're doing. All right, we better move on. We got the homework. There's only 8 of these. I think we'll get through these easy enough. Here we go. Number 1. In this section, we use R to denote the value of the linear correlation coefficient. Right. Why do we refer to this correlation coefficient as being linear? It's kind of a dumb question because it's linear. What are all these things? The term linear refers to a straight line, that passes through the average value? No. Straight line, fraction of the points? No. Straight line, how well fits the data? C. It's C on there. So I guess it is a good question in the end. I knew I picked it for a reason. So there we go. I don't pick them all. I'm picking and choosing out of your homework certain ones. So that one is a good one. It's just making sure you understand what R is. It measures how well the plot fits the straight line pattern. That's what R does. How good is the fit? How linear are the dots? You with me on that? You know, I could probably, I remember my colleague used to teach stats. He had a nice diagram. Let's see if I can draw that out for you. So if you had some dots like this, that would probably be R value maybe 0.8. If you had dots going down, that'd be like negative 0.8. If you had dots going up almost exactly in a straight line, that'd be like 0.95 probably. And if you had dots going down virtually in a nice tight straight line, that'd be negative 0.94 maybe. Get the idea? And if you had dots that were just like crazy random, that would be R basically 0, you know, something like 0.13 or, you know, who knows. Is that making sense on the R? The more they are in a tight line, the closer your R is to positive or negative 1. So R is not the slope, but R tells you how likely it is, how much they fit a line. Not making sense? Now, I remember my colleague used to always do this, and this was a good idea. I remember he had a graph. What if the data looks like this? Now that data is a big U shape, huh? So that data is very much connected, but not in a linear way. So R would still come out about 0. So I want to make sure you're getting this. R is simply testing, do they fit with a line? Now, these data certainly fit. They fit in a U-shaped relationship. And there's other tests for that. And I'm not sure how much we'll get into that. That's more advanced. That's testing for a U-shape. But my point is R is simply testing for a line. And the better those dots fit a line, the closer your R will be to +1 or -1. If it doesn't fit, you know, this fit a line a little more loosely, 0.8, negative 0.8, and then this doesn't fit a line. Now, both these don't fit lines at all. So their R's are basically 0. So that's what R is doing there. So let's go back. Where were we? So that's what R is. It's how well the scatter plot fits a straight line pattern. All right, let's go to number 2. We good with that? To number 2. Okay. So if we find that there is a linear correlation between carbon dioxide, let's read this. What if we find there's a linear correlation between carbon dioxide in our atmosphere and the global temperature? Does that indicate that changes in the concentration of carbon dioxide cause changes in the global temperature? They're trying to trick you. There's one key word in there that's wrecking it. The answer is actually no. What's the bad word in there? The word that's not true. So what if we do a study, okay? And this is very modern, isn't it, right? They're talking about climate change and evidence for climate change. And I tend to think there is some good evidence for climate change based on carbon dioxide anyway. But whatever. So what if you did a bunch of data? What if you did a bunch of data and find out that there was a linear relationship, more carbon dioxide, higher global temperature, seems to fit a line, right? A linear correlation does exist. Yeah, what's the bad word?
Causes.
Yeah, it doesn't mean that it's necessarily, there it is, causes. Remember we talked about that last time. Boy Scouts and, what we do with Boy Scouts? Oh, convicts, right? And milk and cancer and, ice cream and drownings, right? Just because two things are connected doesn't mean they're necessarily connected in a causational way, right? There could be something else causing both those. They have to make other studies to determine that, right? Remember how we talked about all that? So be careful. Be a wise consumer of information. Just because two things are connected doesn't mean one's causing the other, right? So that's what they're trying to make clear there. So that's a no. Does not imply that one causes the other. Okay. Number 3. What is a scatter plot and how does it help us? Remember, scatter plot's a bunch of dots, right? But of course, that's not a very thorough answer. A bunch of dots. But let's see what they want to say. Scatter plot is a table. Is it a table? Is a scatter plot a table? No, it's a graph. Scatter plot is a formula. No, it is not. So it's one of these two, right? It's C or D. A scatter plot's a graph. of a bunch of dots. So a scatter plot is a scatter plot is a graph of qualitative, quantitative. Which one? Yeah, quantity means numbers, doesn't it? Quantity, numbers. Quality is not numbers, right? So D, right? Scatter plot's numbers. It's not quality, right? It's not, strong or, sharp or, those are qualities. It's numbers, quantity, right? Good. We already did that one, huh? So we're on, what number is that one? 4? There's only 8 of these. We're doing well. Okay. Table provided below shows paired data for the heights, presidents, and their main opponents in the election. What a funny thing to put a scatter plot on. So, different presidents' heights, right here, and their opponents' heights. It seems like a funny thing to measure. So, in other words, do people that become president that are taller, did they tend to campaign against their main opponent? Were they also tall or short? Or was there any relationship there? So this is one of those where we've got to go down and look at all the data, which is on the next screen, and see which one fits all those dots. It's tedious. Sorry, I try not to give you too many of these. So here's all the data. Which of those? So here's the so a president that was 186 centimeters tall had an opponent that was 190. So we got to go back or I guess we have it right there. Can you tell?
It's A or B.
How do you know already?
Just because it was scattered, they're too close. It's not going up and down.
Are you just kind of looking at the overall flow?
Yeah.
Let's see.
They all seem too close to each other.
Well, yeah, these are not in any order though, right? They're just kind of all over the place.
What was the F for scatter plot?
Yeah, wants to know which of these 4 is the right scatter plot that fits these data.
Well, I think your first bet in limiting, or taking out C and D is that you would assume there wouldn't be a correlation between.
Yeah, I know. I'm with you. I'm not faking. I think this is a goofy thing to measure, and there's probably nothing.
You could probably. I don't
But I want to be sure. Say it's my test grade on the line. I want to be sure. Could we go? But I bet you're right.
Another linear? I go with the lowest first, the lowest president height I can find.
Oh, good idea. Okay, that's a good idea. I like that.
So
What's the lowest one you can find?
169.
Yeah, 169, 185. Yeah, so let's look for that. 169. So I'm betting A or B also. Let's see. How do these numbers go? Are they going by 5s?
Yeah.
Is that what it is? 165, 170, 175, 180, 185, 190, 195. Yeah, 5s. Okay. So 169 would be about right there, just before. That's the 170 line, right? And what height? 185.
185
And is there another one?
yeah, 175.
How do you? Oh yeah. Good job. I didn't see that one. And 175. So 175 and 185. Yeah. Is this 175?
Mm-hmm.
Yeah. That looks kind of good, doesn't it?
Yeah.
It looks like 175, 180. Yeah, that looks good. Does the B have that?
Nope.
This is like about 169. No, his 2 dots are high. All right, there we go. A, I agree. A it is. Good. So A it is. That was good. Good observation. All right, does there appear to be a relation? No. It's this one. No way. No, that's a kind of a dumb thing to measure. All right, on we go. Where are we at? Did we do that? Is this a different one?
Yeah.
What's this one? Oh, okay. Yeah. Scatter diagram, paired data table to the right. Data is from study comparing amount of tar and carbon monoxide in cigarettes. Use tar for the horizontal, so put tar on the x-axis, and carbon monoxide on the y-axis. Determine whether there appears to be a relation between cigarette tar and carbon monoxide. All right, so here's the data. Is there a relation between cigarette tar and carbon monoxide?
So 1 first.
Oh, good idea. Yeah. So 1. So which data has 1. A and C. Yeah. So B and D are out, huh? A and C. Good one.
And 2, 3.
They're close though. Aren't A and C graphs really similar?
2, 3.
You already got another one?
2, 3.
Okay. Let's see. 2, 3. I can't see much off my screen. Okay, 2, 3 is up there. Yeah, here, let me shrink my screen a little bit.
That would be,
Yeah, 2, 3. Okay, 2, 3. Oh, that looks pretty good for 2, 3, doesn't it?
yeah,
But so, does the other one look good?
that's,
Looks too far. This one's too far. This is like over 3, huh?
yeah.
Yeah, I think it's A. Good? Just a couple points. Get it down. A. All right. Is there a relationship between cigarette tar and carbon monoxide levels?
Yes.
Looks like it. Looks like a line, doesn't it? Yes, the amount of tar increases. The amount of carbon monoxide also increases. Yeah, they increase together, huh? That's right. Good. Looks like it. Okay. Let's see. Number 6. Table lists weights, highway mileage for 7 automobiles. So how much your car weighs and what kind of mileage it gets. What do you think the relationship's going to be? Yeah, more weight, less gas mileage. This is what we call an inverse relationship, right? Yeah, so we're guessing this one right off the bat, huh? Right? Right? The more your car weighs, the less the gas mileage. Probably. Probably. That would be our guess. Does that fit the data? I bet it does. So let's see. Can we grab a point or two?
So we're 22? 22 first?
22 here. Highway mileage 22. And the weight is 4465. Yeah, this looks like 4465, 22. This looks like this dot right here, huh? Yeah, that looks good. Yeah, it's got to be B. It's got to be B. Is there a linear relationship?
Yes.
It's one of these yeses. Which one is it?
The weight increase, highway mileage decrease.
The highway mileage. Oh, increases?
No, decrease.
Yeah, decreases. Yeah, so decrease. Yeah, C. Yep. Good. Easy on that. All right, on we go. So for a data set of brain volumes, so how big your brain is, and IQ scores, what do you think? Bigger brain, higher IQ, or does that not matter at all?
Doesn't matter.
Doesn't matter?
Separate measurements.
So they're measuring brain volume, how big your brain is, and your IQ. They're wondering, is there a relationship?
No, because the p-value
No, what was the p-value? Oh, there it is, yeah,
is
p-value.
31%, 31.2%.
Yeah, p-value 0.3, so that's 31.2% chance of what?
Of it being
Luck, right? That's the chance of luck. So if they found any connection, it could have just been luck, right? That's a pretty good chance of luck. You want that below 5% to say evidence is strong. So we're thinking no, p-value, blah, 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 31.2%, which is high. That's a high value. So there is, or is not sufficient evidence to conclude that there is a linear relationship. That's just too high. We don't believe it. Okay, number 8. For a data set of weights, pounds, and highway fuel consumption, miles per gallon, of 8 types of automobile, the linear correlation coefficient is found in the p-value is 0.042.
4.2%, yes.
Write a statement that interprets p-value conclusion about linear correlation. Yeah, right. So this, move it over, right? We always take that 0.042, move it 2 places. 4.2%,
25?
which is low, bless you. Which is low, so there is sufficient evidence. That's strong evidence, isn't it?
Thank you.
That's strong evidence to conclude that there is a relationship between how much the car weighs and the miles per gallon. That's strong evidence on that. Because when a p-value is below 5%. Is that making sense?